Hi, everyone. So we're very happy to have D.Grady from Wichita State University, who is going to tell us about deformation classes of invertible field theories and the Freed-Hopkins conjecture. Dan, please.
Okay, thanks very much, Hisham. Thanks again to the organizers. It's a pleasure to be here, and it's a great opportunity to give a talk.
Again.
Well, again, yes, I was here for 4 years, about 5 years ago. Okay. So I want to start just with a little background on this paper by Freed and Hopkins on invertible field theories. Specifically, I want to just kind of talk about what their motivation was. They were trying to understand the moduli stack of quantum systems with a fixed symmetry type HD, where HD is some compact Lie group. And, well, the applications that they had in mind were to condense matter physics. And specifically, the models there are these lattice systems. And the thing is, I mean, if you want to understand the moduli stack, well, you need some sort of axioms for these lattice systems in order to get a handle on what exactly the moduli stack looks like. So there's no real good axioms for those lattice systems, but we do have axioms for topological field theories, for Euclidean field theories. And Freed and Hopkins had this idea, which was, well, let's kind of apply this heuristic principle that if you look at the low energy physics of a gapped system, it should be approximated by a topological field theory. So what I mean by gapped here is if you look at the minimum energy eigenvalue of the Hamiltonian, then it should be an isolated point in the spectrum of the Hamiltonian operator. And the other heuristic principle is that the homotopy type of the moduli stack, so the moduli space, well, that should be determined by the low energy behavior. Okay. And then the idea is, well, now for these axioms, what are the axioms we're going to use? Let's wick rotate our quantum field theories to the Euclidean setting, and then we can use Siegel's axioms to try to understand the moduli space of the low energy effective theory. So that's sort of the guiding principle that Freed and Hopkins worked with to try to compute really they're interested in the connected components of the moduli space, they call the deformation classes of those quantum systems. And in this setting, unitarity of the theory manifests itself when you wick rotate as reflection positivity. So I'm going to talk later about what reflection positivity is. But let me first give you their main theorem here. So the main theorem of this paper is that, well, if you look at deformation classes of reflection positive invertible, d-dimensional extended topological field theories with a fixed symmetry type, then you can compute the deformation classes as homotopy classes of maps. Well, here you have some spectrum. This is the Thom spectrum that's associated to a stable so you have these Lie groups that include into one another, and you take the co-limit as this parameter d goes to infinity. And so there's the Thom spectrum associated to that. And yeah, if you take the torsion subgroup, so this gadget here is some spectrum, which I'll talk a little bit about later. But just think of this as some fancy cohomology of the Thom spectrum. If you take the torsion subgroup of that, well, that gives you these deformation classes of topological field theories, invertible, reflection positive. So that's their main theorem. Yeah, so here MTH, this is just the Thom spectrum. And okay, this other spectrum is the Anderson dual of the sphere, or rather a shift of the Anderson dual of the sphere. I'm not going to talk too much about this spectrum. I mean, if you want, just think of just cohomology with z coefficients, the Eilenberg-MacLane spectrum, and that's kind of a good substitute intuitively for thinking about what this thing is, but that's not quite what it is. Okay, so, and then the conjecture. So now it becomes a conjecture. There's the theorem. The conjecture is that, well, there's a similar isomorphism here. If you remove the torsion, if you pass from the torsion subgroup to the full group here, and you remove topological field, the adjective topological here on the left side, then you still have an isomorphism between those two things, a bijective correspondence. So this is a conjecture, I think, because, I mean, they kind of work with this ansatz that they expect this Thom spectrum to still model the deformation or the homotopy type of the Bordism category with even geometric structure. But they don't have access to a Bordism category with geometric structure. So I think the first holdup is that they didn't really have access to this Bordism category. And the second holdup is that you have to promote this spectrum here. Well, you need to somehow include the geometry. And I mean, it's not clear how to do that. I mean, I'll say more about this later, but there's sort of two problems that kind of prevented them, I think, from proving the conjecture. And really, it's about the geometry, including the geometry. So I'll say more about this later. But before I do, I want to do a toy example, which I think kind of really helps to understand the meaning of this theorem, especially the right side. Okay, so the toy example, let's just consider a one-dimensional sigma model with a target manifold, which I'm going to call X. Okay, so in terms of functorial field theories, what I have is just a map from a zero-dimensional manifold, which is a finite disjoint union of points, a compact manifold, so finite disjoint union of points, and you're going to map into X. So you pick some points in X, and then you have a Bordism that goes between those points, so a bunch of paths, and you have to assign to it a linear map. So in particular, you assign to a point, you have to assign that to a vector space, right? And then to every path in X, you have to assign a corresponding linear map between those vector spaces, right? That's what a functorial field theory does. So if you require that you want this data to vary smoothly, then you have a smooth family of vector spaces parameterized by the points in X. And then also you have these linear maps, which show you how to connect the fibers. And that's exactly transport data for a connection on a vector bundle. Okay, so in particular, a field theory, one-dimensional field theory like this gives you a vector bundle with connection. And it turns out that you can actually go the other way. If you have a vector bundle with connection, you can also produce a field theory from that data, basically because the field theory has to be symmetric monoidal. So once you say what happens to a single point, you'd say what happens to disjoint unions of points. When you know what happens to a path, you say what happens to disjoint unions of paths, and then there's just a little bit of data left, which tells you what to do for duals. So you have evaluation and co-evaluation maps, and they have to go to certain maps. They have to go to the evaluation, well, the usual evaluation map and co-evaluation map for a duality between finite dimensional vector spaces. So everything is determined by just this data here. And actually, even more is true. So recently, Dan Burrick-Evans and Dmitry Pavlov, they showed that, in fact, the whole moduli stack of functorial field theories, so here you have the one-dimensional Bordism category with this target X, and the target category here for your field theories is just the category of vector spaces. Well, this is equivalent to the moduli stack of vector bundles with connection on the manifold X. Okay? Well, inside this moduli stack of field theories, you could consider a more constrained class. You could say, well, let's not consider all field theories, but let's just consider the ones where we want the transport functor to only depend on the homotopy class of the path. And in this case, well, I would call that a topological field theory. Some people might call this first one a topological field theory because there's no metrics, but I want to think of a topological field theory as being one which is homotopy invariant. So here, in this case, if I insist that this only depends on the class or the path, then, well, the corresponding vector bundle that you would get under this equivalence is going to be a flat vector bundle. Okay, so now let me explain what this has to do with this Freed-Hopkins conjecture as a toy example. So if I consider the subcategory in the category of vector spaces, finite dimensional, let's consider the subcategory of just invertible finite dimensional vector spaces. So those are just lines, complex lines. Vector spaces are over C. Then, well, if you look at this previous, if you look at the inclusion of flat, so right here, this is the moduli stack of flat line bundles, right? You have discrete topology on C cross here. And so if you take the isomorphism classes, that just gives you H1 with coefficients in the units of C. And you can include those isomorphism classes into all classes of field theories. So now we don't just have flat bundles, but we take all line bundles with connection. This here is the moduli stack of line bundles with connection. And this right vertical map here, well, this takes the deformation classes. Basically, you're looking at just the homotopy type of the stack of line bundles with connection, which is a KZ2. And here you just, so you map to cohomology in degree 2 in Z by taking deformation classes here. So now this composite here, it's exactly the Bach-Stein homomorphism for the long exact sequence induced by the exponential sequence. And the image of this is the torsion subgroup here. Okay, so the point I'm trying to make is that the analogy that you should think of when you compare this with Freed-Hopkins' main theorem is that, well, this is something like the isomorphism classes of the topological field theories, and if you take their deformation classes, you get this torsion subgroup. And they expect that, well, if you take all of them, you should just get all, well, in this case, just all of H2. But in their setup, they have this funny Anderson dual and all this stuff. So morally, this is kind of what's going on here. So any questions on this before I continue? The toy example. Yeah, so I think that's a good example to kind of keep in mind to have, to understand their theorem. So now let me talk more about the setup. So let me talk a little bit about reflection positivity for these field theories. Okay, so let me fix a symmetry type. So let's take a compact Lie group, HD, and a representation. So OD, that's the orthogonal group. And I'm going to require that the image of this representation contains at least the connected component, the identity here. And basically, this is because the original theory, if it was Lorentz invariant, when you Wick rotate, you expect to at least see the special orthogonal group in the image. It may be the whole thing if you had reflections to begin with. And you can show, Freed and Hopkins proved this in their paper. So when D, the dimension is greater than 3, and when the image of the representation is SOD, then, well, this compact Lie group looks pretty understandable. It just looks like a product. So you take spin D, the double cover of SO, and you take a product with the kernel of this representation here. And then you quotient by the cyclic subgroup that's generated by this central element, which squares to 1, squares to the identity here. Okay. And so that quotient, yeah. So all those Lie groups look like that. And then they define what an HD structure on their Bordisms are. So it's just a reduction of the structure group of the frame bundle to HD. Okay, so you have a HD subbundle, or equivalently, you can think of it as a lift. B is going to be your Bordism. You have the frame bundle, the classifying map of the frame bundle, and then if you lift this against the representation here, and this diagram commutes up to a homotopy, such a lift and a homotopy is what the reduction of the structure group is. Okay, so that's the type of structure they have on their boardisms. Okay, so, all right, so now for the reflection part. So there's an involution on the boardism category, and the involution comes from, well, one way to get it is to fix a hyperplane reflection. So a priori it will look like it depends on this choice of hyperplane reflection, but you can actually remove this dependency by doing the construction a slightly different way. I'm not going to do that because this is just a bit easier, and it doesn't actually matter that it depends on this reflection anyway. But in my setup, this beta will depend on the reflection. So if you fix a hyperplane reflection, then there's a corresponding automorphism of HD. What is the automorphism of HD? Well, here's HD here. Well, you take your reflection and then you lift it to pin plus, the double cover of OD, and then you act by conjugation on the spin factor here. So, and since sigma was a reflection, this is a Z2 action. It squares to the identity. So that's this automorphism here. And, well, this automorphism then induces an involution on the boardism category in the following way. So you take, well, what is a boardism? A boardism is really a pair. B is the base manifold, the boardism itself, and then you have a principal bundle, a subbundle of the frame bundle. And how do you act on this boardism? Well, you just fix the boardism data, don't change the base. And in fact, the total space of the bundle is also the same, but you change the action of HD on the total space. And the way it changes is by precomposing the action with this automorphism that you got from this choice of hyperplane reflection. Okay, so what a reflection structure is on a field theory is, well, it's basically a Z2 equivariant functor that goes from the boardism category to vector spaces, and here on vector spaces, I'm taking complex conjugation as the Z2 action. But it is still a structure and not just a condition because there's an isomorphism that exhibits the equivariance. So in other words, you first do beta and then you do the field theory, and that's supposed to just correspond to complex conjugation on the vector space side. Okay, so that's what a reflection structure is. Okay, and if you have a field theory with reflection structure, then there's a corresponding Hermitian form. So, oh, actually, let me say one thing here. Let me draw a picture on the whiteboard here because I need to, there's another way to think about this involution in terms of duals. Okay, so let me first draw a boardism. Let me draw a one-dimensional boardism here. So imagine you have, okay, this is a boardism between two zero manifolds here. And the data is, well, you have a principal bundle. Here it's kind of trivial, but you also have an arrow of time, which is how Freed-Hopkins described this. And this is an orientation, a normal orientation. So you have this boardism that sits inside this interval, and you choose a normal direction here. So this is a boardism from, this is like, well, in the topological case, this is the identity boardism, because you can contract the whole thing to just the starting point here. But there's also, well, that's not all you can do. You can also have, you can reverse the arrow of time, say on the target here. So you have a picture like this, and now it's a boardism not from this point to this point, but 2 points to the empty. So think of in the middle here, you have the empty boardism. But notice that here, you reverse this arrow of time. So this is the evaluation map for a duality. right? You have, let me call this Bordism Y. Let's call this Y dual. Okay, and you have the evaluation map, which goes to the monoidal unit. In this case, monoidal unit is just the empty Bordism. So, so why am I bringing this up? Well, this beta involution is related to this, this duality that's given by reversing the arrow of time. If you take your principal bundle, so here, also maybe I should say that the Bordism itself is not really just a point, but rather it's like a small germ of this point inside the ambient one manifold here, and the same on this side. And if you take the principal bundle on Y, and then you pull back by the orientation reversing diffeomorphism here, which reverses the arrow of time, then it gives you exactly this other principal bundle that I called P prime up there. So in other words, another way to describe this action is it sends a Bordism to its dual. And those two involutions are isomorphic, but they're not exactly equal. So, yes, it depends on the choice of sigma. Yeah, exactly. Yeah. Yeah, and beta here depends on sigma, so yeah. Oh, yes, yes.
So typically reflection positivity is something what acts on the manifold itself, and you kind of have some local version of reflection positivity. Is that right to see it like that? Because the reflection positivity from like 80 years ago, this was take Euclidean space, take one coordinate and flip it, and then make some statement about some correlation functions behaving whatever.
Yeah, so you mean that this is more of a local construction
Yeah.
rather? Yeah, so that, it is. Yeah, so it's different, I think, slightly. I mean, I'm not sure how it relates to this classical perspective that you're talking about, but in the Freed-Hopkins setup, it is, yeah, I mean, just something that happens on this small germ of the Bordism that when you know, well, I mean, it's an involution on the entire Bordism category.
It's like
so.
on tangent spaces more, isn't it? So because...
Can you say that again?
Isn't it something on tangent spaces? Because on B itself, you don't touch it, but then you have these bundles and these bundles.
Yeah,
These bundles have some kind of, they come from a structure group reduction from the tangent bundle, so it's like in the tangent bundle, like flipping one direction to minus the direction.
Yeah,
in the tangent bundle, yeah.
The OD is the frame.
Yeah, the OD is the frame, and
so
you
it's
just
local in the frame at this point.
yes.
Thank you.
That's right, yeah. But you can think of it two ways. Either you can do this, where you just act on the principal bundle itself by this involution or by this automorphism, or you can do this thing where you pass from the manifold or the Bordism to its dual and pull back the principal bundle, and the two are related. They're isomorphic. So, any other questions? Okay, so now that I've said that this beta is related to this action by taking duals on the Bordism category, so there's a Hermitian form here that's induced by this isomorphism. And the way you get it is you take, well, here is your vector space that's associated to your Bordism, and here's this complex conjugate. You just use the isomorphism here to get to the thing with beta. And then this one, as I said before, it's related to taking the dual of the Bordism. And those two are isomorphic in the Bordism category, so you compose with that. And then finally here at the end, you use the evaluation map. And the composition is this Hermitian form now. If it's positive definite, then we say that the field theory is positive. So the reflection structure is given by the involution, and then the positive part of reflection positive is given by the positivity of this Hermitian form, positive definiteness. How much time do I have? Okay, good. Okay, so now let me go to the fully extended setting. So, I mean, basically what I want to do to go to the fully extended setting is I want to replace the one category of vector spaces by some kind of higher category. And I'm first of all, I should say I'm in the invertible case. So instead of taking vector spaces or finite dimensional vector spaces, I'm going to take just lines, complex lines. And when I go to the fully extended case, I want some kind of higher categorical replacement for this category of lines. And Freed-Hopkins choose this Anderson dual, or rather a shift of the Anderson dual. And they provide a little bit of justification for why you can think of this as being like higher lines. But I think a better justification for this as a target, and they also have this, this too. So it's sort of a universal target for field theories in the sense that they're determined by just their partition function. So this Anderson dual satisfies a universal property. And if you unpackage what that universal property means, if you take it as a target, well, it just ends up telling you that the whole field theory is determined by exactly what its partition function is. So what it assigns to a closed manifold. So it'll assign a closed manifold to some number, and yeah, everything's determined by that. So we're going to think of this as just like a kind of jazz up version of the one category of complex lines. And then the point is, well, the homotopy type of the fully extended Bordism category, it can be computed as a suspension of a spectrum called the Madsen-Tillman spectrum. This was originally done in for not the fully extended case, but just the ordinary category of cobordisms. Its homotopy type was determined by Galatius, Madsen, Tillman, and Weiss. And then Chris Schummer-Priest later, he has this paper, it's not published still, but he has this result where it extends the theorem to the fully extended case, and you just get a suspension, a default suspension of the Madsen-Tillman spectrum. Okay, so now we can start to see how the ingredients on the right side of this theorem are kind of emerging. So the idea is that if you take a field theory with target given by this shift of the Anderson dual, what I'm going to do is think of this as, so if I take a spectrum and I take its connective cover, I want to think about this as being a Picard infinity groupoid. I want to think of it as a symmetric monoidal infinity groupoid, and all the objects are also invertible. So not just morphisms, but objects are invertible. So if I think of a spectrum that way, then when you map into something like that, well, mapping into something like that is the same as, such maps are equivalent to just maps out of the thing that you get by formally adding, or formally inverting all morphisms and all objects. So this is the, I mean, well, when they say the homotopy type here, really what you're doing is just this construction, formally inverting all morphisms and all objects in the Bordism category, and the result is a spectrum, and that spectrum is this shift of the Madsen-Tillman spectrum. So it's a group completion, yeah. Yeah, so it's homotopy group completion. But now it's at the level of not an infinity 1 category, but an infinity D category. So you first invert all morphisms, and then finally you invert objects at the end. So yeah, so the point is any field theory like this canonically factors through this group completion. And the space of all those maps here from this corner to this corner is the same as the space of maps between the Bordism category and the target. And then the involution that we just talked about, this beta involution, it induces an involution on the spectrum by just, I mean, this construction is functorial, so you just apply the construction to the involution and it induces an involution here. All right, so that's sort of how you're seeing these ingredients emerge on this right side of the classification theorem. Yeah. And now let me say something about this Anderson dual. So the Anderson dual sits in a long exact sequence like this. So there's an exponential sequence the exponential sequence induces this sequence the same way it would on ordinary cohomology with coefficients in C and C, units of C here. And then complex conjugation, well, that gives you a Z2 action on, this is the Brown-Kamenetz dual associated to C. In this case, it's just the Eilenberg-MacLane spectrum. And so complex conjugation gives you an action there. Well, you want to get an action, a corresponding action on this, the Anderson dual, and also we're going to need one on this here, the Brown-Kamenetz dual associated to this group of units of C. And well, the thing is, there's not a canonical choice of action on either of those. The space of actions for which this map here is equivariant is not contractible. But it's pretty easy to understand. It splits as a finite disjoint union of connected components. And you just need to say which connected component you want to take. And there's a sort of a preferred choice that Freed and Hopkins make. And their choice basically comes from drawing an analogy with what happens for the category of Hermitian vector spaces. There are two involutions on Hermitian vector spaces. One takes the dual, and the other one takes the complex conjugate. And because of the Hermitian structure, the composition of those two involutions trivializes. So basically they say, well, we want to choose the connected component where the Z2 actions kind of behave like this, this involution, this composition of involutions which trivialize. And so they call those the real structures on this Anderson dual. And they call this action, this choice, well, they actually choose an element in this connected component, which they call gamma, and that's an action on a Z2 action on this spectrum, which is related to the complex conjugate action on this Eilenberg-MacLane spectrum here. Okay, so then with all of this setup, yeah, the idea is, well, now if we look at those let's just take reflection structure. So we're gonna try to understand the space of those reflection theories. Well, the deformation classes should be, I just explained that when we take this target, the Anderson dual here, well, we factor through the group completion. And now here, I'm going to take equivariant maps because I want them to satisfy this reflection. I want them to have reflection structure. So I'm just going to take the equivariant maps here. And here I just needed, well, here we had that involution beta. And here I needed a Z2 action, which is morally like doing complex conjugation. And that's the setup they have. So these Z2 equivariant maps are well, they compute the space of all those maps is the space of reflection theories. So I'm not going to discuss positivity, mainly because I just don't have time to do it. But I do want to say something about how, so what I'm going to explain in the rest of the talk is how to prove this, this conjecture. So what I need to do is explain how to get to this point. So starting from field theories, how can I mean, kind of morally we understand how we're supposed to get this as the reflection theories, but I need to tell you, well, I need to explain the geometry that I'm going to put on Bordisms, so enhancing things to geometric structure, and also I have to kind of modify this target so it includes the geometry, and then after taking deformation classes, I want to produce maps like this. So I'm going to explain that in the rest of the talk. And then there's a way to go from here to get not just reflective field theories that have reflection structure, but also you want positivity. And the way that Freed and Hopkins do this is by computing, they do a very non-trivial calculation in stable homotopy theory. There's some homotopy fiber that they need to compute, and the computation leads them to, well, magically this turns into, you stabilize here. So you have these inclusions of groups, HD into HD plus 1 into HD plus 2, and you stabilize, take the co-limit. And then also the suspension kind of falls out. It just gets dropped in this calculation. Now, in my setup, you can reuse this exact calculation to get to the positivity part of reflection positivity. So basically the idea is once you've shown that the reflection theories are what you want them to be, you can define positive theories the same way. Well, it's roughly the same way. There's some modifications to make, but basically following Freed-Hopkins' definition of positive, you can do it with all the geometry. And then you can reuse the calculation to prove that the deformation classes of those are the same as what they have. So that's another reason why I'm going to omit this, because you can just reuse their calculation for it. Okay, so so now let me explain how to get the reflection theories. All right, so first, without the equivariance, there's a map from this map in the long exact sequence that's induced by the exponential sequence. It induces a map on homotopy classes like this, so just mapping into this map here. And this one, so here C, the units of C have the discrete topology. Here again, think of this toy example that we had at the beginning, where these are like the topological field theories, the isomorphism classes of topological field theories. And then if I take the image here under this connecting map, well, the image should be the torsion subgroup here. Okay. So, and then you should have the same thing equivariantly. So if you add the Z2 actions, then you should have a map, and again, you'll get the torsion subgroup. Okay, so now finally, let me explain how we're gonna try to prove this. Well, not we, but how I tried to prove this theorem. So basically, two things need to be done. First, we need to enhance this HD structure that Freed and Hopkins have to some kind of a differential HD structure. So now I want to include connections on the bundles. And also I want this sort of geometric refinement of the Anderson dual here. And once we've done this, then the next step is to compute the deformation classes. So I need an analogous statement that Christian-Reprise has. So when I take the group completion of the Bordism category, now a geometric structure, I need it to be the suspension of the Madsen-Tillman spectrum. And then also when I take deformations of this smooth spectrum, I need to get the Anderson dual. So that's what we need to do. Let me state the theorem, and then I'll explain how to prove at least the middle one. So all of these spaces are isomorphic in the homotopy category of spaces. Yes?
The previous slide you said you have to enhance it to connections.
Yes.
Is that obvious from definition, or that's a choice?
Well, have to is a strong word. I would say that's what we're choosing to do. That's what Freed and Hopkins want in their definition for geometric structure. But there's a lot of structures we could consider, yeah, that are kind of geometric enhancements. In fact, this third bullet point here, it turns out that even if you take flat structures, HD structures, then it's still equivalent. And this seems like it shouldn't work because, I mean, the moduli space of flat bundles is very different than the moduli space of bundles with the moduli stack of bundles with connection. But here what happens is, so maybe I'll explain this a bit. It's a consequence of the geometric cobordism hypothesis that these two spaces are the same. So what happens is, if you evaluate, functorial field theories are determined by their value at a point. So what I want to look at is just the moduli stack of points in the Bordism category in bullet point 3. So what does the moduli stack of points look like? Well, what's a point in the Bordism category? A point is really a coordinate cross in RD. Because we remember a small germ, so think of a small open ball around the origin here. So RD is sort of the ambient manifold, and then the point lives at, say, the origin, and you have this little open ball on which the geometric structure lives. But we don't just have this one point, we also have smooth families, as Dimitri explained in his talk. We have these smooth families sort of built into the Bordism category. So in terms of the ambient manifold of the point, we really have RD, and then we take a product with this Cartesian space U. So there's an open subset of Rn for some n, which is diffeomorphic to Rn. So we have this smooth family of points, and then let's compute or see what we get when we we compute this, so we evaluate this geometric structure on this object in, well, it's an object in this category that Dimitri explained, FemD. So what do we get? Well, here we're taking fiber-wise flat structures on RD. So, I mean, on the fiber, I mean, you just have a flat bundle on RD. You can trivialize the flat bundle with connection by a connection-preserving isomorphism. And then you just have the automorphisms. The automorphisms just look like elements of the Lie group HD. And now you take smooth families. And when you take smooth families, you don't just see elements in HD, but you see smooth maps from this U into HD. Smooth families of elements in HD as automorphisms. So you have the classifying space of the group of smooth maps from U into HD. So the point I'm trying to make with this calculation is that here, if you take the deformation space, so that's like, so here you have smooth structure, and taking the deformation space sort of forgets the smooth structure and just remembers the topological. More precisely, what you do is you plug in here for U extended simplices, and you take a colimit over the simplicial diagram that you get by taking the simplicial maps or the face and degeneracy maps between the extended simplices. So it glues together a space for you. And this space will see the whole homotopy type of BHD. It won't just see discrete BHD. It sees the whole homotopy type when you take the deformation space. And that's morally why that equivalence works there. Okay, so how much time do I have?
About 7 minutes.
Okay, so are any questions? I'm very behind, it seems, so. I thought I would have too little slides, but I think I have too many. Well, Dimitri talked a bit about this setup. So the geometric structures for abordisms live on this site FemD, and the objects in FemD are submersions with d-dimensional fibers, and the morphisms between them are fiber-wise open embeddings. And the geometric structure that I'm going to take on my bordisms is a pullback. I'm going to take a pullback diagram like this. This pullback diagram lives in the category of sheaves, simplicial pre-sheaves on FemD. And so here, this is just the moduli stack of fiber-wise principal HD bundles with connection. This is the moduli stack of vector bundles with connection. This is the sheaf, so it's a discrete simplicial pre-sheaf, of fiber-wise Riemannian metrics, which Dimitri explained is a pre-sheaf on this category of MD. This map here is the Levi-Civita connection. So by the fundamental theorem of Riemannian geometry, there's a natural transformation like this from the sheaf of fiber-wise Riemannian metrics to vector bundles with connection. And you take this homotopy pullback diagram, and then if you look at, say, a vertex in this homotopy pullback, well, what is it? It's going to give you a Riemannian metric, fiber-wise Riemannian metric, a principal HD bundle with connection, and you have an isomorphism. So you also have this map depends on a representation of HD. So this map takes the associated vector bundle and its associated connection. And then you have an isomorphism here in the moduli stack of vector bundles with connection. And that's really exactly like adding connections into the setup to this reduction of structure group that Freed-Hopkins have. And we also, it's important to have these metrics around too. We want them in the case of non-topological field theories. Okay, so, okay, again, there's a choice of hyperplane reflection gives you an automorphism of this moduli stack now. And again, it gives you an involution on the bordism category. So all this works, I mean, basically the same way it does in the topological setup. You just have to worry about the connections, and you can show that everything goes through. Basically, you just end up taking, at the level of Lie algebras, you have the adjoint representation. That's how the action acts on one forms. So, and then, this object, so now for the target, so this is how this is now our Bordism category that I'm working with here, the one that Dimitri briefly sketched. And so so now we have the geometry on Bordisms. The next step is we need to enhance the target to have geometry. And the way that we do that is, so I'm going to take a sheaf of spectra now instead of just an ordinary spectrum. The sheaf of spectra will live on the site of Cartesian spaces. These are the base spaces for our families of Bordisms, if you want. And it turns out you can do exactly the same construction that you do for the ordinary Brown-Kamenetz dual, just in this category of sheaves of spectra. There's a Brown representabilities theorem that works for any presentable stable infinity category. And you can find this in the work of Pachkoria and Stragowski. They have a paper where they prove this. And the Brown representability theorem says that, well, here's the functor that's being represented on the right side here. So you assign a spectrum, it's a sheaf of spectra now. You take its sheaves of homotopy groups in degree 0, stable homotopy groups in degree 0, and then you take homomorphisms of sheaves of abelian groups here, and this is the smooth units of C. So you take the units of C, but now you're remembering the fact that it's a smooth manifold. So you take this homomorphism in sheaves of abelian groups, and this spectrum represents that functor. So yeah, and then there's a Z2 action. This is similar to the Z2 action that Freed-Hopkins have on the Anderson dual, and you can do basically the same kind of idea to get a Z2 action on this kind of geometric version. I'm calling this a geometric version of the Anderson dual. But we want this, well, when we take the suspension, the default suspension, I'd like the deformation space of this to be the Anderson dual. So, well, what is the deformation space? Probably I'm running low on time. Okay, I'll try to finish up. So the deformation space, well, there's a functor that goes from sheaves of spectra to just ordinary spectra. It's left adjoint to the inclusion from spectra into here, which takes locally constant spectra, sheaves of spectra. And well, this smooth, doing things now in sheaves of spectra, so again have a long homotopy fiber sequence, it's again induced by the exponential sequence in the same way it is in the topological case. And what I'm going to do, what I mean by deformation space is I'm going to apply this shape, it's called the shape functor, to this sequence. And well, what happens is that since the smooth complex numbers you can retract them, there's a deformation retract, just a straight line deformation retract to the origin. It's a deformation retract through group homomorphisms. And when you apply the shape, well, you can use the universal property of the Anderson dual, and you conclude that this one is contractible when you take the shape because of this deformation retraction. So then the long homotopy fiber cofiber sequence, the shape will preserve it because you use, well, the usual arguments that you have for stability. The cofiber sequences are also fiber sequences. The shape is a left adjoint, it preserves cofiber sequences, which are also fiber sequences, and you get that the whole sequence goes through when you apply the shape. And then one of this piece is contractible, so this map has to be an equivalence. So you do see that the deformation space is the shift of the Anderson dual. And I think I'll have to skip some stuff in the interest of time, but maybe just to kind of outline the very end here. So, I mean, once you have promoted all these structures to include the geometry, then the calculation itself, which proves that the deformation space is what you want, is actually very formal. So, I mean, all you do is you just, so this part here is just coming from this adjunction. This is the homotopy group completion. The vertical bars are here. And then you apply the shape functor, which is taking the deformation space. And then here we've already computed it as the shift of the Anderson dual here. And here, the shape of this geometric Bordism category, oh, this part requires a proof, But we proved this, well, we proved half of this in the geometric cobordism hypothesis. If you replace this structure here by the flat principal HD bundles, then we proved in my paper with Dmitry Pavlov, we proved that this is this shift of the Madsen-Tillman spectrum. And then you have to make an argument for why it's the same as this with the connections. So I do that in my paper, but that's the only non-trivial part in this calculation. And then the rest of it, so then, I mean, that's the end of the proof right here. And then here, I mean, the topological theories, if you take the discrete topology on the units of C, okay, again, if you take connected components here, you look at the induced map on connected components, then, and you look at the image, you see the torsion subgroup, which is Freed-Hopkins result. So I think I'm gonna probably stop there. I'm sure I'm out of time, so yeah, thank you.
Thank you. Any further questions for Dan? Nito?
Your result that you're getting all the invertible theories, not just the topological ones, is predicated on the fact that for the topological ones, you have the Anderson dual, the C-star Anderson dual, right? Because you're just sort of bootstrapping on that result to get the integer.
Yes, essentially. So the result, I mean, there was no, and Freed-Hopkins acknowledged this in the paper, the real hang-up is that there wasn't, they need to see the topology on the units of C in order to get this, to compute the deformation classes in general. And they have just the discrete topology because in spaces, I mean, it's not, you can't really see the smooth structure. So,
no, but even then, the invertible topological theories being equivalent to the Anderson dual, is that result something you prove or you use? Is it even there in the literature?
No, Freed-Hopkins proved that when you take topological.
Yeah, but I thought they conjectured that.
So there's a theorem and there's a conjecture. The theorem, let's go back to the beginning here. Okay, here's the theorem. So what they prove is that if you take topological field theories, you get the torsion subgroup here. What's a conjecture is that if you remove the word torsion, then you don't have, and topological here, it's still an isomorphism. So here, the reason why this is a theorem and not a conjecture, I mean, it's still kind of, okay. Well, yeah, it's a theorem because they have the default suspension of the discrete units of C as the target. And if they look at the image in here, they know it's the torsion subgroup. So the reason why this one, the second one's a conjecture, is because they don't have access to the smooth structure on the units of C, which you would need that in order to show that the deformation space is this Anderson dual. And then the second reason is because on bordisms, they want some geometry, and they don't have a bordism category which has geometric structure.
What confuses me is that there's a recent unpublished result of Theo Johnson-Fried and David Reuter that says that invertible topological theories is the C-star Anderson dual. So it's this result without the torsion. So how could they be proving a result that's already been
it's
proven?
a little bit different though, because if you take the C-star Anderson dual.
That's what they prove.
Yeah, that's different though. Here, you're not taking the C-star Anderson dual. It's the.
No, my problem is that if you're claiming this result of Freed and Hopkins is a theorem, then what are Theo Johnson-Fried and David Reuter proving?
So are you saying that you think the theorem is, well, first of all, this one has deformation classes.
I see. Maybe that's the catch.
And it may be true that what year was the paper?
It's not even, I mean, this is unpublished. They're talking about it. Maybe
okay.
deformation is the issue, that they're showing that you
Well,
can
if you
even
take C star as the target here, then you would expect to see topological field theories and remove the word deformation, so isomorphism classes.
I think their result is that there's a universal linear category that deloops vect all the way up, and if you take the Picard groupoid off that category, you get the Anderson dual of C star. That's their result.
Okay, yeah, but that would still be topological.
That's all topological,
Yeah,
yes.
and that's because again, it's this discrete topology on C star that's showing up. Yeah, so I think here the difference is one, there's deformation classes,
Maybe that's what it
which
is.
is why we have this Anderson dual. It's not C star here, it's Z, and again that's because you're seeing, well, if you take smooth C star and you take the deformation space, you see this one instead of the brown combinate dual for C star. So.
Okay. Any other questions for Dan? Did you want to quickly say something about the part you skipped? If you want. If there were questions during your talk, I think you get a little more time, if you want.
Oh, okay. Let's see. So toward the end here,
Yeah, that part.
here's the part I skipped. Yeah, so this is what we prove this is what I proved with Dmitry Pavlov in this paper, the geometric cobordism hypothesis. So if you take the shape, so first take the homotopy group completion of the bordism category. And again, the structure here is these flat, fiber-wise flat structures. You take the shape and you get this suspension of the Madsen-Tillman spectrum. This can be proved using the geometric cobordism hypothesis. Actually, just the topological cobordism hypothesis here. So the step that was the non-trivial step in the next calculation is showing that this canonical map, where you include the flat structures into all these geometric structures where you have connections on those principal bundles, you need to show that it induces an equivalence like this. And to prove this, you have to, it turns out to be slightly delicate, but it kind of has a flavor of the H principle, Gromov's H principle. So, so basically you have to, instead of taking deformations of the whole bordism category, you kind of want to commute the deformations inside to just the geometric structure. And then you have to show that sort of the deformation space of this is the same as this, and it requires a calculation that, the calculation amounts to showing that you have two sheaves on Cartesian spaces, and you want to prove that, that it induces an isomorphism on relative concordance classes. And if you know this, it's enough, or this is enough to conclude that the homotopy type of the two sheaves is the same. So taking the shape is the same. In fact, that same kind of idea is used in the paper of Galatius, Madsen, Tillman, and Weiss when they compute the homotopy type of the cobordism category. So that's sort of how I go about proving this equivalence.
Very good. Any other questions? Okay, let's thank Dan again for the very nice talk. Thank you, Dan.